The Strategic Innovation Fund is investing £450 million in energy network innovation, because the challenge of rapidly decarbonising our energy networks is enormous. But we can do this. With collaboration, we can make the leap. A giant leap together. We need the bravest, brightest, boldest change makers from across the world to work with Innovate UK, Ofgem and the Strategic Innovation Fund to create the energy networks of the future. The best ideas targeted at the most pressing challenges that reduce emissions and save consumers money. Join us now. Take a giant leap together with the Strategic Innovation Fund at ofgem.gov.uk.
Hello, everyone, and thank you very much for joining us. My name is Matt Hastings. I'm the Deputy Director for the Strategic Innovation Fund at Innovate UK. Thanks for coming together for what promises to be an insightful set of show and tells.
Matt, you've managed to get on mute there.
I think I'm being muted from afar. Let me start that again. So, hello everybody, and thank you very much for joining us. My name is Matt Hastings. I'm the Deputy Director for the Strategic Innovation Fund at Innovate UK. Thank you for joining us for what promises to be an insightful set of show and tells covering the SIF Discovery Transport Challenge projects. I'd like to start by sending a huge thanks to all of the participating energy networks, especially the innovation teams and their third-party partners who have put in the graft during the last few months. We really, really appreciate all the hard work that you've put in. Now, as with any new process, it can take you out of your comfort zone at times. There can be a few niggles and areas for improvement, but you have embraced this new Strategic Innovation Fund mechanism head on, and for this we're hugely grateful. Now, the fund has a very clear vision to deliver net zero at lowest cost to consumers and turn the UK into the Silicon Valley of energy. And whilst it's hard to say given the current external environment, we do feel we can make the UK the best place in the world to be an energy consumer and the best place in the world to be an energy entrepreneur. Supporting UK consumers and driving business growth to deliver net zero is why we are all here. Our mission has three key pillars: strategic alignment with other funders and other sectors, delivering fully in agile, not just the challenges, the discovery alpha beta mechanism, but also the way in which the whole SIF team operates as a unit, and critically to focus on business as usual and commercialization. We are trying to discover the new products and services of the future that will benefit consumers, drive down emissions. It's all about consumers, planet and business. And this really is the purpose of the fund. And as per the animation, you know, we're on this giant leap together towards decarbonisation. None of us have a monopoly on great ideas. Working together across the sector is how we will succeed. And Giant Leap Together, as it's affectionately called, has these four key phases. Challenge setting, and you will have seen recently we released our round 2 challenges for launch in September. Targeted ideation, where we point great ideas at great networks. Incubation, where networks can build award-winning consortia. And acceleration, where the challenges open up, and we will join the ENA, Ofgem, BEIS, networks and others in hosting the first ever UK Energy Innovation Summit on the 28th and 29th of September in Glasgow. The round 1 discovery projects you're about to hear from are in acceleration. And if you talk to some of the teams who've been delivering, they'll recognise it's been quite intense. But speed is essential here. We need to move quickly. We need to take risks. We need to deliver the value consumers are looking for as fast as humanly possible. And let's pause a little bit to talk about the F word, failure. Some of these projects will fail, and that is not a dirty word. That's not a bad thing. That's the very nature of discovery. These projects should not be judged negatively if they fail, quite the opposite. A positive failure to us equals a quick learning. It equals a faster route to finding the best solution. And instead of just fail fast, we prefer learn fast. And that is what the SIF is all about as well. Finally, I just wanted to thank the Innovate UK team. David Richardson, Kate Jones and Manu Ravishankar from the innovation team, and Christine Kunick, Tom Poole and Amy Oswin on the PMO, as well as Paul Whittemore on comms. Also, a big thanks to our monitoring officers and to the work of the expert panels and assessors. They've all worked incredibly hard to support the discovery phase, and without them and without you, our network colleagues and partners, we would not be in a position to deliver the SIF. So thank you all for all your hard work to get to this point. The best is yet to come. I'll now hand over to Kate. Kate, over to you.
Yesterday. So I sort of nipped down there, see if I can get them this morning.
I'm getting a wee bit of feedback, so I wonder if just everyone can go on mute there. That would be great. I don't want your conversation in the recording there, so thank you. Good morning, everyone. Good morning, everyone. Like Matt says, I am an innovation lead in the Strategic Innovation Fund. You're in for a treat today. We're talking all things transport. So our first transport challenge was open to the transmission electricity networks and the gas networks. And it's all focused on how the networks can develop the infrastructure required to support and accelerate zero emission transport. So like Matt mentioned, these projects have now completed the discovery round, and that's really the feasibility round for the idea. And it's about understanding the size of the prize and identifying if the project should progress to the next stage. So a big congratulations to all the project teams for getting to this stage. So in terms of housekeeping today, the format that we have is we have a chunk of projects that we'll do together that are grouped by themes. To help if I went to the next slide so you could see the themes. Here we go. And what we'll do is we'll take Q&As or questions in the chat, and we'll pick them up at the end of a block of projects. So if you've got any questions, please put them in the chat throughout, and we'll pick them up at the end. The session is recorded, so you will get access to the slides and the information that we've shared. And if we don't get to any of the questions, we'll do a wee follow-up just to share anything that we have there. So let's crack on. So to start with then, I'm going to be handing over to Colin McNaught from Ricardo.
Good morning, everybody. Thank you, Kate. Thank you, Matt. My pleasure to be taking the first slot in this morning's session on the transport projects and to present to you our discovery project on a holistic hardened approach to heavy duty transport, or H2H for short. So can I have the next slide, please, Kate? So I'm going to go through the project team and the steering group, the project rationale, the discovery project, the results that we came from our 8-week discovery, and then what happens next if we proceed to the next round. So can I have the next slide, please, Kate? So with the project team led by Scottish Power Energy Networks, as they were the transmission electric company who gave us access to the funding stream provided by Ofgem and Innovate UK. Network Rail as the rail infrastructure owner, ourselves, particularly the energy and the rail teams within Ricardo, and working with our academic partners at the University of Leeds. Our steering group included the project team, plus Transport Scotland and ScotRail to cover the policy and the rolling stock aspects of the railway and the solutions that we were looking at during discovery. So that's the broad team that we involved. Can I have the next slide, please? So starting with what's the current plan? So the electrification to decarbonise rail, which is the main drive for solutions to get to remove diesel trains from the UK railway, is to add new full electrification. So connecting typically to transmission network, providing power through a feeder station to 40, 50, 60 kilometres of line, and those distributed across the network. At the moment, rail demand's about 1.45 terawatt hours, so a little bit over 1.5% of total UK electric demand. HSH1 phase 1 will add about another 1.2, and our estimate of the impact if all of the diesel lines that are expected to be moved to full electrification, I would add about another 3 terawatt hours, so just short of 9, which would be around about 3% of current UK electric demand. And the key point is that that is a lot of demand which is tied to the rail timetable. It's inflexible demand, which is running against, I guess, the current thinking around how we need to have a flexible energy system. So in H2H, we looked at 3 alternative options. So if I can have the next slide, please. The first was to look at trackside batteries. So the conventional solution, but with a battery system buffering the grid connection to the railway. The second option was discrete electrification with a battery on the train. So in this case, we don't electrify all of the track, but we potentially provide around about 10 kilometers every 40-50 kilometers or so to be able to recharge the train battery as it passes under a short section overhead line. Requires a little bit more storage by the trackside to cope with the peak demand to recharge the battery on the train, as well as power it through those 10-kilometer stretches. And then the alternative we looked at was hydrogen. So either direct connection of renewables to hydrogen production or potentially using grid electricity, storing hydrogen either at the hydrogen production site or at the rail depot, and then refueling at the depot to provide the trains with fuel for the coming day service. So that's the concepts we looked at. Can I have the next slide, please? So the things that were driving us towards this were that full electrification has a high capital cost, well known that it's an expensive thing to do. And since the rail decarbonisation strategy was looked at a couple of years ago, we are in a slightly different situation, excuse me, that costs are obviously a concern to the railway, given competition with other modes and the lower passenger ridership numbers. So full electrification obviously adds a very substantial fixed cost, capital cost at the beginning, and then operating and maintenance costs through the long-term life of those assets. As mentioned earlier, we are, if we think about the full electrification option, adding a substantial amount of fixed demand that's inflexible, unlike the other sectors of transport like EVs, which will have probably more flexible charging. And we noted that in 2020, there was a curtailment of about 3.8 terawatt hours, so quite a similar number to the additional railway demand that they were planning to add. And that cost consumers £243 million, around about £8.5 per household. So if we can be more flexible in our electrification decarbonisation of the railway, then perhaps we can access some of those savings for customers. And the final thing is that these solutions require a more collaborative and smarter solution. Historically, the relationship, I think, between the electricity industry and the rail industry has been rather transactional about using standard solutions. And to the point that was made by Matt, we need to be working collaboratively on these kind of solutions. Can I have the next slide, please? Thank you. So why did we choose Scotland? Several reasons. For the railway, the plan to remove diesel passenger trains is a little bit earlier, 5 years earlier in 2035. Scotland's railway has always had a more holistic approach between the infrastructure operators, Network Rail, and the train operating company, ScotRail. And now that ScotRail has moved into public ownership, now they are both public sector organisations. So having a collaborative, integrated, holistic solution has therefore got some better baselines to be able to work on. And as the map shows, there are a number of lines that are going to be electrified fully planned, which are the ones in the red, but the ones in the green and the yellow are not planned for full electrification under the current proposals. So there are a number of lines that need an alternative solution, and therefore we've looked at a couple of those, as you'll see in a moment. From the energy sector point of view, Scotland has higher ambitions for renewables and hydrogen, and a lot of the Scottish power is already produced from renewables. Plus, there are also more constraints on renewables, so the benefits of flexibility and being able to release some wind farm constraints would be more realisable in Scotland earlier than perhaps in other parts of the UK. So can I have the next slide, please? So zooming in at the 2 lines we chose, so the first one is the line from Inverness to Thurso and Wick, which is 280 single track kilometres, quite a rural route, taking some quite long excursions inland to avoid high gradients. Relatively rural, so a relatively modest number of bridge interventions, which are costly for full electrification. And we looked at that line, the traffic, the substations as part of our assessment. Next slide, please. The second line we looked at is slightly shorter. It's from Girvan on the southwest corner of Scotland down to Stranraer. The plan is, under the current proposals, to electrify fully from Glasgow to Ayr and then Girvan, but not to continue the further 65 kilometres south. Quite a large number of bridges here because it's a slightly more populated area than the line north of Inverness. So those are the two that we chose to give us hopefully two examples that would explore the different solutions and see whether we came out with some conclusions. So kind of next slide, please. So we undertook a large amount of data collection and stakeholder consultation, including obviously the project partners, but we also talked to two other of the discovery projects, the Hubs project, which is led by University of Leeds, and we are a partner in that as well. And you'll hear about that next. And then the rail decarbonisation planning project, which I think you're going to hear about third in today's session. So we've tried to share insights and ideas with the relevant discovery projects in this early phase. We also spoke to providers of hydrogen trains, companies involved in the practical aspects of electrification, so that we got a good grasp of some of the costs and problems that might need to be addressed in some of these ideas. And we also happily, there was the first rail conference in Scotland post-COVID, and managed to make a lot of contacts and get a lot of insights from the delegates and speakers at that key conference. Next slide, please. So this is the net present value result that we got to for the Inverness to Thurso and Wick line, using the data that we collected from a range of sources. So at the bottom, this is on a 30-year, 3.5% discount rate basis. So the bottom section is the diesel, showing the train capex. Because the other options include a new train to be on a like-for-like basis, we included a new diesel train, even though that's obviously not going to happen in practice. But to make it like-for-like, we included that. The train OPEX and the fuel, there's no infrastructure because there's no overhead line, the blue, which appears a little bit later. Full electrification, we estimate was around about £1.4 billion, dominated by the overhead line infrastructure needed for 280 kilometres of single track, but also quite a substantial amount of ongoing operation and maintenance costs over the 30-year period to keep that safe and operating for the railway. Discrete electrification, we assumed 6 stretches of 10 kilometres of discrete electrification. We did not at this stage pin down exactly the location of those, but that was based on the total route and the likely kind of performance of the trains. Maybe that we could do a little bit less of that, but it obviously does have an impact on the capital cost of the infrastructure and the operating cost, but it still didn't quite match what we came up for as a number for hydrogen. And we started to look at that in more intensely, because obviously when you get a result that shows you that one option's coming out strongly better than the others, you start to examine the numbers in more detail. So we went back and looked at the train costs, we looked at the hydrogen costs and revised them slightly upwards. And this is the revised version with slightly more pessimistic costs, and it was still substantially cheaper than the other options that we looked at. So if I can have the next slide, please. This is the equivalent results for the shorter Girvan to Stranraer line. So the numbers are all smaller because it's 65 kilometres, not 280. But the pecking order, if you like, is similar. And that was interesting because we had thought that the battery solution might come out quite positive for Girvan Stranraer. This is with 2 sections of 10 kilometres of discrete electrification. One closer to Girvan and one closer to Stranraer. There's quite a substantial gradient as you move southwards from Girvan, and therefore we thought we were going to likely to need 2 sections. But even with only 20 kilometres of overhead line, it still comes out slightly more expensive. We presented this to the stakeholder group, and one of the feedbacks was that, well, actually, given it's 65 kilometres, which times 2 is 130, some of the proposed new battery trains might be able to make that return leg without actually having the electrification at all, and therefore remove the 20 kilometres overhead line. So we did a sensitivity analysis, looked at that, which is the next slide, please. Next slide, please. Oh. Yeah, sorry, that's okay. I've described that. Next one. Thank you. So sensitivity, no, that's the one. So as you can see, the battery train with no overhead line on the right-hand side does come out cheaper than the hydrogen option. We had to change one or two of the other numbers in this because to make it like for like, if we are assuming the train is coming from Glasgow under wires as far as Girvan, we had to include the fuel cost for the entire line. So some of the other numbers are moved up to represent the fact that the like-for-like comparison using electricity all the way is therefore in the other fuels as well. So this shows that the battery train without overhead line becomes about half the price of the hydrogen on that 30-year 3.5% NPV basis, and therefore was the result that we chose to take forward and think about more in Alpha. So if I can have the next slide, please. We took a qualitative review of the flexibility aspects. We would need to do a detailed half-hour analysis of demand to be able to do a financial cost-benefit analysis of the flexibility benefits to the electricity sector. But we did a qualitative review looking at which of the flexibility services that are currently in the UK electricity market could be accessed by the hydrogen or the battery solutions, and that showed that the majority of those would be accessible by the scale of system that we had in mind. And if we proceed to Alpha, one of the key things will be to quantify that by using more detailed time series analysis of the electricity demand for the trains, and therefore the impact on hydrogen production or the battery storage by the trackside. If I can have the next and final slide, please. So our next steps are twofold. The green hydrogen fueling solution for hydrogen electric trains is the lowest cost for the Far North Line, and that remains the case under the sensitivity analysis that we've done so far. So in Alpha, we propose to assess the full benefits of that, particularly focusing on the flexibility aspects of the green hydrogen production, and to run through some of the more practical aspects to make sure that there are no major practical barriers or costs that be missed in the initial 8-week discovery phase. For the battery trains, that's the lowest cost option for the Girvan to Stranraer line as covered, but it does assume that the battery trains that could be procured in a few years' time have that range and have that range over there over the life of the battery system. And that's one of the cases that was considered in the parallel hubs project that Leeds are using and was presented next. And we decided that it was more sensible to take that line and that idea and incorporate it within the hubs project, which is the next presentation. So there's a continuity and some collaboration through that route. So I hope that was a useful introduction to our project. Look forward to hearing your questions, and I'll pass back to Kate and to the team at Leeds. Thank you very much.
Thanks, Colin. So just in case anyone missed the start, if we can put any questions in the chat box for now, what we're going to do is we're keeping the themes together, and then we're doing questions at the end. For now, I will hand over to Professor Lee and Nick Fletcher from the University of Leeds to speak about the other rail project that Colin mentioned.
Brilliant. Thank you very much, Kate. Good morning, everyone. I'm Nick Fletcher from the University of Leeds, Business Development Manager at the Institute for High Speed Rail. I'll be turning my camera off because I had some problems with it this morning, so I don't want to be freezing and you're losing any contact and so forth. So I think, thank you very much, Colin, for mentioning us in your presentation as well. I'd like to start by first mentioning that our partners that are involved in this project. So obviously we've got Scottish Power Engine Networks, Ricardo and Network Rail were our partners for the discovery phase. And similar lines to what you just heard in the previous presentation, we're going to look at the basic concepts and approach to the discovery project that we've just done, the summary of this information that we found, and potential next steps as well. But I think it's worth considering first, before we launch into the project itself, it's worth highlighting and reminding some of the audience of some of the key figures around power usage, consumption, etc. within the rail sector. So as most of you are probably aware, as I think Colin's already referred to, railways are a single large electricity user, consuming over 4 terawatt hours of electricity per annum. There is still 60% of existing track which is non-electrified, and over 2,400 kilometres of that is unsuitable for electrification. 2.8 million tonnes of CO2 is produced per annum from freight and passenger trains within the UK. And obviously we're all aware that the UK government is trying to phase out diesel trains by 2040, 2035 in Scotland. And obviously, given the number of stations that we have within the UK, there are large untapped resources, unused roof space, land space for renewables, energy storage to benefit both the railway network and the power grid itself. And obviously, one of the key things as well is that redeveloping railway stations is high on the agenda of not just the UK, but European cities as well. And so we're looking at trying to look at these and explore potentials and benefits for energy efficiency and energy flexibility around said stations. So if we go on to the next slide, please, Kate. Thank you. So what is the Hubs project and our approach to the discovery phase? Well, Hubs is basically looking at how we can bring together the renewables, the hydrogen supply, etc., around these railway stations. Now, within the UK, there are 2,500 stations. Now, not all of them will be applicable to the Hubs model that we're suggesting here, but we're going to be looking at what we can do to the vast majority possible to these stations here. We like to think that this is the first of a kind around these stations, and also these will be able to link cities and communities across the country to support green mobility and the future requirements of the power grid from there. There are two major driving factors of the energy hubs. Obviously, one is to reduce the carbon emissions of the rail stations and to make them carbon neutral. The other is to retain the financial competitiveness in the transport industry compared to other means of transportation. Such, there are 4 key elements, or if you like, technology pillars to our approach. First of all, there's machine learning assisted digital twin technology. This gains us insights into energy flows, provide predictive energy management and improving overall energy efficiency. Secondly, there's a wide area optimal planning and operation coordination framework to network and integrate hub flexibilities and enhance rail power supply resilience and provide services to the power grid. We then have advanced control technology, which will entail the integration of local renewable generation, the recovery of train braking energy, and supporting vehicle to station, vehicle to grid, and hub to grid. And then finally, we have an advanced management control framework to effectively deliver optimal real-time performance while maintaining robustness and fault tolerance of the hubs. If we can go on to the next slide, please, Kate. So again, we looked at a considerable number of stations, predominantly in Scotland. And again, we tried to look at, as some of you may be aware, different classifications of stations. So not just those with a high volume of footfall, but those sort of rural stations as well, which might be applicable from that set. So as you can see from here, we looked at 7 different stations altogether. And if you just click once more, please, Kate. We looked at a number of different scenarios because obviously one size will not fit all. And each of these scenarios builds on the other. So obviously the first one is looking at station roof photovoltaics and battery storage, adding on to that then car park PV canopy and so on until you get to scenario number 4 here. And again, we looked at various sort of scenarios where we could apply these for here. If we could go on to the next slide, please, Kate. Oh, sorry, can you go back one, Kate? Okay, sorry, my mistake. Yeah, the next one, please. Sorry. Yeah, so what we're going to show you here now is the first of 2 stations that the team, Professor Kang and the team looked at. The first being Haymarket Station here. So we looked at the status quo and how the application of the 4 scenarios that you've just seen might impact this station. So with the application of scenario 1, which is the roof PV and battery storage, you can already see the OPEX and carbon footprint has fallen, whether in the island mode or not. In the second scenario, we included, obviously, this is scenario 1, and then building on that, the car park PV canopy. Obviously, you can see the CapEx has increased to just over $500,000, but at the same time, the OPEX has fallen to nearly a third in both cases, and the payback period is 4.7 years in one instance there. The final one, scenario 3, which is the recommended design, which results in a net zero station, you can see again here that the considerable fall in terms of the OPEX from that side there. So the cost benefit analysis shows that the example payback period of the first 3 hub designs for a busy urban station is about between 4.7 and 7.6 years in the context of the increased tariffs. If we could just pop on to the next one, please, Kate. And again, this is on the route that Colin was talking about to Girvan and Stranraer. This is the rural station. This is Bar Hill. And again, here, this is one which is deemed unsuitable for electrification. So our energy hub design can recharge and refill batteries and hybrid trains with optimal payback time of about 12.6 years. So this avoids expensive electrification investment for those rural sort of infrequent rail tracks. If we can go on to the next one, please, Kate. Okay. So, as you can see, several things came out from the actual discovery phase that the team conducted. So in 2020 to 21, they 10,000 kilometres of the total, almost 16,000 kilometres of the UK's rail routes are not electrified, accounting for a share of 62% of the trains running by using diesel. To decarbonise the track which cannot be electrified, the Energy Hub technology can provide total capital cost savings of about £2.3 billion if the energy hubs are used to recharge and refuel battery or hybrid trains. On the second point, so the UK's annual non-traction load is 440 gigawatts per hour and costs around about 48 million. If the energy hubs are built for all stations and depots, because again, this could be applied to depots as well as stations, the annual OPEX saving can reach as high as 32.8 million with the increased tariff. In the UK, there are 343 large railway stations, which can provide more than 600 megawatts of power. The scaled annual cost of firm frequency response is £22,000 per megawatt hour, which represents 13.2 million additional revenue if the hubs offer ancillary services to the power grid. So it's not just taking from the grid, it's giving back to the grid as well. The rollout of energy hubs to all stations would lead to an annual reduction in carbon emissions in the UK by approximately 3 million tonnes of CO2. All 4 design scenarios have suggested the payback period for the optimal hub design is between 4.7 to 12.6 years, depending on which scenario you choose. As I said before, there's not one scenario which fits every station. We have to be, allow for variations in the station design, layout, etc. For busy urban stations, scenario 3 is obviously recommended, which offers deep decarbonisation and better efficiency with the payback period as stated before of 7.6 years. And obviously the last 2 points here, particularly the last point, obviously these kinds of, this technology, or this idea can be further utilised in stations on London Underground, HS2 potentially, and electric road systems as well. In terms of looking ahead, obviously, as Colin's mentioned, we're looking at talking about sort of the Ayr, Girvan, sort of Stranraer route. And there are three key points here that we're potentially looking at within the alpha phase. So with the Ayr to Girvan, the overhead line in place, but there is a need to increase and strengthen the station's capacity, power capacity, requiring a new feeder station. So again, the cost of that is quite extensive. So by comparison, the hubs would be a tenth of that price, roughly £2 million, and the payback would be about 12.6 years. The second key point is for the Girvan Stranraer, which is not electrified. The H2H project demonstrated cost savings via battery usage, and the building of hubs along with this would support battery charging. Plus, electrifying the route and additional feeder stations would cost around about £100 million. So the building of 3 hubs would be less than about a tenth of that from that side. And the final point, obviously, we consulted with our partners quite closely on this, and obviously recommendations from them and Network Rail as to the best way forward within the alpha phase here. We have new partners coming on board for the alpha phase, and obviously we're looking for any additional interest or members who would be interested in part of the industry advisory board moving forward from there. So I think that's all from the lead side. Okay, thank you.
Thanks, Nick. Again, we've got a couple more projects to go before we're going on to Q&A. So if there is anything in the chat, we'll come back to that. We're going to ask people to answer the questions out loud. I know that there's some answering in the chat, but just for the recording purposes. So what I'm also going to do, I'm just going to quickly stop sharing my screen because I think you guys are hearing every time somebody joins a meeting. So hopefully you won't hear that now. So Can somebody just confirm they can still see the slides? A thumbs up would be great.
Yeah, that's fine, Kate.
Yeah.
Great, thanks. Okay, so now I'm going to hand over for the rail decarbonisation project. Sarah, am I coming to you directly first?
Yes, you are.
Great, okay. And again, if there's any questions, just pop them in the chat and we'll get on to them in just a minute.
Morning, everyone. I'm Sarah Buckley, and I'm presenting on behalf of EA Technology about our SIF rail decarbonisation planning project. Next slide, please. So yeah, the agenda today is what is the actual problem to be solved, what we did in the discovery phase, and then obviously moving on to our next steps and the overall conclusion and points to take away from this. Okay, next slide, please. Okay, so obviously we've discussed in the previous presentations, the UK government, as part of its pathway to net zero, has developed a transport decarbonisation plan, and this sets out the need to decarbonise rail transport and removal of all diesel trains from the network by 2040. This will only happen if there is an overarching strategic approach to identify the most appropriate technology to be deployed for certain parts of the rail network. The main strategy for achieving net zero will be the electrification of existing routes. But as we know, particularly in rural and remote areas, this may not be possible. Therefore, the development of alternative technologies such as hydrogen and battery will be key to achieving decarbonisation of the rail network. There is currently no consistent mechanism for identifying the most appropriate, cost-effective and carbon-efficient technologies for certain parts of the network that considers the availability of electricity and hydrogen along the rail routes. So this is a critical issue which will impact on the solutions available for certain parts of the network, ensuring the most cost-effective investment. Next slide, please. So this discovery phase was in response, obviously, to the net zero 2050 goal, as it's developed detailed plans for decarbonisation across the UK, including the Traction Decarbonised Network Strategy, as well as regionally, such as Eastern Region Traction Power Strategy. To date, these plans have been developed with minimal consideration to the available capacity on the electricity and gas networks. And the purpose of this project, funded through Ofgem, was to consider the rail industry's plans whilst assessing the constraints and opportunities for both the electrical and hydrogen power supplies. The initial discovery phase of this project aimed to highlight the challenges with the existing approach and opportunities for a more coordinated planning and investment process. And on the screen, our partners were Fraser Nash leading on the hydrogen element of this project, EA led on the electrical and overarching implementation plan. Obviously Northern Gas were the lead on this project, Evershot Rail, Network Rail and UK Power Networks. Next slide, please. So due to the proposed scale of electrification across the UK, the approach for the electrification side of this was to take a deeper dive into the case study area of Tees Valley, northeast of England. This area has a mixture of significant stakeholders relevant to the decarbonisation of the rail industry and provide a natural opportunity to assess the feasibility of hydrogen power trains where electrification may not be the best solution. The East Coast Main Line, which runs between London and Edinburgh, is electrified. However, significant sections of the railway around Middlesbrough or Teesport are major freight corridors operated by diesel power only. The initial approach for the analysis of hydrogen need was to also focus on the northeast of England, but due to the much smaller contribution shown by the Traction Decarbonised Network Strategy, this was expanded to also show scaled up numbers at a national level. The analysis undertaken during this discovery phase has required collaboration across the rail and energy sectors to understand the ambitions and challenges that decarbonisation presents. In addition, we had open discussions with other relevant SIF projects to share learnings and to avoid any duplication. The relationships formed during the discovery phase will continue and develop further during any further project phases. Next slide, please. So what was discovered? Significant work has already been done to determine the best approach to decarbonise the rail industry. However, I've already said before, minimal consideration was given to the available capacity on the energy networks. The discovery phase has reaffirmed that investment and decarbonisation plans across the three sectors are not aligned and have been pretty much developed in isolation. This could lead to inefficiencies, missed opportunities for carbon savings, potentially wasted investment, and a lack of coordination from investing partners. To meet the 2050 targets in the eastern region alone, it is estimated that the length of electrified track will have doubled and power requirements more than triple. Depending on the level of electrification works that are carried out, the need for hydrogen varies significantly, both in quantity and where it is needed. The estimated demand for hydrogen by 2040 varies between 16,700 tonnes to 64,000 tonnes of hydrogen per annum. To put this into context, 64 tonnes of hydrogen per annum is nearly 4 times the amount proposed in the original Traction Decarbonised Network strategy, 9% of the current national hydrogen production, and over double the current amount produced via electrolysis. Hydrogen is also an energy-intensive fuel to produce, so a greater reliance on hydrogen to fuel the railways brings a steep increase, approximately 3 times greater in the electrical demand to produce the hydrogen compared with a purely electrical power supply. Regardless of which low carbon solution is adopted, decarbonisation of the rail network will add significant demand to the energy networks. And all major new electricity demand connections of significant size are competing for capacity in a highly competitive and dynamic market, and therefore the headroom available is continuously changing. Any project program needs to allow sufficient timescales for these works, noting that these have long lead times and require interaction with multiple stakeholders. Also to consider is that the level costs and timescales for electrification on the rail network remain uncertain, and therefore further work is required to determine the most viable option to decarbonise specific parts of the rail network. Next slide, please. The gaps that remain is that the greatest challenge to replace diesel rolling stock with the greatest challenge is to replace diesel rolling stock with cleaner, more environmentally friendly forms of traction power. With a proportion of the current diesel rolling stock approaching its end of life, there is an urgent need for the rail industry to develop a viable strategy for fleet replacement. There is a significant level of uncertainty regarding the level of electrification that is likely to occur due to the affordability and timescales of delivery, therefore requiring the rail industry to find other viable low-carbon solutions to replace diesel fleets. Hydrogen fuel cells power being an obvious choice for many of them. Hydrogen fuel cell powered trains are a viable and technically feasible option to replace many diesel-powered vehicles. However, they have limited use cases and so are not suited to high-speed passenger services or freight services in particular. Despite such challenges, the distribution of hydrogen becomes a key factor in making hydrogen-powered trains operationally useful. Depending on the level of electrification that will be achieved, the need for hydrogen varies significantly and where it will be needed. Further work is required to understand the whole life costs of different electrification system types versus alternative traction power technologies, including the most cost-effective methods for generation and delivery of hydrogen to where it is needed. This requires collaboration from all three sectors to develop a data-driven methodology that can determine the least regret options to achieve rail decarbonisation in the required timescales. Investment and decarbonisation plans across the three sectors are not aligned, not only due to a lack of coordination, but due to misaligned price control periods. The DNOs have already set out their business plans for the next price control period up to 2028, where no consideration has been given to the rail industry's electrification plans. Collaboration between all three sectors is required to reduce the impact of misaligned price controls and for the rail industry to meet the 2050 targets. Next slide, please. After reviewing the work done to date, it's clear that closer coordination between the energy networks and rail industry, in combination with a more analytical approach, is required to assess the optimal interim and long-term rail decarbonisation solutions. From the discovery phase, it was found that the current decarbonisation plans are in the most part developed in isolation without utilisation of optioneering tools that can encapsulate the coordinated short-term and long-term benefits across the rail sectors. It is also clear that these plans have been developed on the basis of historic interactions with minimal consideration how changing energy landscape will impact other sectors. Therefore, next slide, please. An alpha phase is needed to showcase how a collaborative data-driven approach can improve efficiency of decarbonisation planning and demonstrate the cross-sector considerations that will need to be made in future infrastructure and investment plans. This will identify least regret opportunities in the electricity, gas and rail sectors for coordinated investment to accelerate rail decarbonisation at lowest costs to GB energy consumers. An optioneering tool will be developed to identify the optimum, intermediate and long-term decarbonisation options available, considering whole life costings. The decarbonisation solutions that will be considered are electrification, partial electrification with battery technology, local electrolysis hydrogen production, and hydrogen production at scale remotely and then distributed to the railway by pipeline, and then continued use of diesel up to 2040 or switching to green diesel. Next slide, please. The primary outputs will be an optioneering tool comparing the decarbonisation options across a selected case study region Tees Valley, and then proposing a beta phase business case. The tool will enable the rail industry and energy networks to align infrastructure investment in a cost-effective way that will deliver decarbonisation of rail. It is envisaged that following a similar methodology, the tool will be able to be scaled for deployment across the UK, factoring in local rail and energy infrastructure developments, utilisation forecasts and specific needs. The beta phase will separately take the recommendations from this tool to identify where a demonstrated project offers the greatest potential to gain whole system experience of operating a pilot hydrogen train fleet and least regrets opportunity for Northern Gas Networks and other stakeholders in the region. At this stage, the primary users are considered to be the energy networks and rail industry, but there is also potential for interest from renewable generators, hydrogen production facilities and other emerging sectors in a hydrogen fuel source. Next slide, please. The benefits of this will be through the development of a cross-sector decision support tool that will enable cost-optimised decisions to be made when considering what decarbonised options are available to replace the existing diesel trains with net zero replacements. In general, the coordinated approach will lead to improved infrastructure investment planning to identify efficient investment opportunities that reduce expenditure and stimulate the hydrogen supply chain. Accelerated decarbonisation of the rail industry through efficient planning and utilisation of existing infrastructure, and a cost-efficient, low-carbon, reliable rail industry benefiting consumers, industry and the wider economy. The wider impacts, although the optioneering tool is specifically focused on decarbonisation of rail transport, our project will generate learning that is relevant to other sectors. In particular, as infrastructure for hydrogen is developed, other users and industries will need to ensure that there is a fit with their own business requirements and location. Our tool could potentially be adapted to support their decision making. Next slide, please. And to conclude, the discovery phase has found that investment and decarbonisation plans across the three core sectors are not aligned to date. The level costs and timescales for electrification on the rail network remain uncertain. The demand for hydrogen varies significantly, both in quantity required and where it is needed, and a coordinated approach is required to meet decarbonisation targets on time and in the most cost-efficient way. An alpha phase will develop a data-driven methodology that can determine the least regrets options to achieve rail decarbonisation in the required timeframes and at lowest cost to GB energy consumers and rail network users. And it will leverage the stakeholder relationships across all three sectors and expertise of project partners. And that's it. Thank you very much.
Thanks, Sarah. Thank you very much for that. Just swapping screens. Okay. We've got one more project for us. It is a different theme slightly, so we're going on to road transport, but we'll be handing over to William Darby from Element Energy. And then at the end, we've got 20 minutes to go through questions from all four, and I'll invite all the speakers and lead networks to put their videos back on, and we'll do some Q&As. So, William, I'll hand over to you.
Great. Thanks very much, Kate. Yeah, so as she's already said, Will Darby from Element Energy, coming up last, but hopefully not least. So I'm here to talk to you today basically about our hydrogen transport study for the north of England, specifically focused on multimodal transport for road. So if you can take us to the next slide, I'll just outline the sort of work package summaries. So there's sort of three sequential work packages that I'll talk through, and then the fourth one around the sort of stakeholder analysis before going on to the alpha phase scoping. There seems to have something's gone a bit wrong with the formatting here, but if you can carry on. So specifically, as I said, in terms of outlining the work packages, we developed this along three sort of consecutive work packages around fuel cell vehicle deployments initially, and then looking at the refueling requirements for those vehicle deployments before looking at plans for hydrogen production and supply. And then alongside that, we, as a group, you can see the core kind of group along the bottom there, Element, Northern Gas Networks, Transport for the North, Durham, Heriot Watt and Everschultz and Rise as the technology providers, and we went out and spoke to a number of the other SIFs and a number of the sort of industry stakeholders part of this project. So if you can go on to the next slide, I'll talk a little bit about the summary and findings from work package 1. So the first thing to do then was to down select the vehicle types that were included in our study, and we basically decided as a group based on things like vehicle use cases, vehicle availability, the capacity of those vehicles to drive hydrogen demand, and other, I suppose, using factors, and concluded that we would select buses, trucks, refuse collection vehicles and port handling equipment. We considered trains. Obviously, there are a number of other SIFs considering the train market, and due to the time, effectively, we decided to leave out things like trains, ships and air because effectively they are large enough and kind of point sources of demand that don't quite overlap so much. So that plans for Alpha will be to consider those potentially in the next phase. So if you can go to the next slide, what we did with the help of Heriot Watt and TfN was build on something called the Athena modelling tool, which took the locations of the depots of these various transport modes, so buses, HGVs, ports, refuse collection vehicles, and mapped them in the northern region, so the Northern Powerhouse 11 region. And what you can see on the left is a sort of prediction for an early rollout phase of point sources of hydrogen demand, and in a mature phase in 2040 what we estimated it'll look like. And what you can see, I guess, less clearly possibly in the rollout, but certainly starting more clearly, is that the demand is, as expected, likely to emerge around sort of the major conurbations in the north. And while initially these kind of modes are fairly going to be scattered, as we get to a more mature phase, freight is likely to dominate in the road transport sections. So if you can go on to the next phase then, next slide, sorry, yeah, that's more or less kind of just summarising what I've just told you. So things like ports are great sources for hydrogen demand. And effectively, if you're looking at demand emerging in the early phases and looking to build stations there, then stations built around those sort of early demands are likely to kind of continue to be well used as demand grows around city clusters. So if you can go on to the next slide, please. So what the next part of this was then is the Athena tool takes into account data on the routes of HGVs and a number of the other vehicles and tries to assign optimally located hydrogen refueling stations to try and scale up their size, whilst obviously taking into account kind of real world detour constraints. So on the left there, you can see the mature phases demands for fueling, and on the right you can see a network of HRSs that is meeting that demand. And if you go on to the next slide, one of the kind of key findings from our phase was we did some modelling around hydrogen stations. And a key sort of early learning from hydrogen transport rollout has been that small stations struggle to be economic, and larger stations, whilst improving economies, as you can see in the graph in the bottom, the cost contribution goes down with the larger station and a larger utilisation. You also get higher reliability. So there's a real economic driver for operators to shift slightly their diesel behaviour patterns, certainly in HGV sectors where they might have fueling on their depot. There's an economic driver to find these kind of optimally located stations where a number of operators can share these refueling facilities and significantly reduce their fueling costs. So if you take us on to the next slide, then I'll talk a bit about the production and supply. So I've set out effectively so far the sort of demand that's emerging for transport, how we can meet that with refueling stations. And I think a key point of this project is about ensuring that there is effective kind of coordination and planning between the strategic road network and the gas network. So one point that's a fairly strongly emerging conclusion is that we are transitioning towards a hydrogen economy. On the left there, you can see a map from the Department of Business, Energy, Industry and Strategy around the number of hydrogen projects developing around the UK. And what you can see is there's basically a disproportionate number being developed in the north of England. And to facilitate that, the gas networks are starting to respond with plans for dedicated hydrogen pipelines and their supply. So it's talked about a lot, effectively, the gas network converting to hydrogen. Part of this project's kind of learnings and engagement with the likes of Northern and Cadent and National Grid was to understand how actually this is going to take place. So initially, it'll be sort of local distribution networks around those major point sources of production. And the map on the right shows a sort of larger plan for a dedicated hydrogen transmission and distribution network that looks to join those stations up. And so if you go on to the next slide, then what we tried to do was to join up the transport mode, I guess, which is work packages 1 and 2, with the hydrogen production and supply modes, which is work package 3. So the Athena modelling tool kind of absorbed those data inputs, and we modelled 4 kind of station supply scenarios. So you've got a rollout phase for sort of 2027 with stations predominantly supplied by the incumbent tube trailer, truck and trailer technology, and then 3 sort of mature phases where the model kind of compared and contrasted stations provided with only tube trailer and on-site production versus stations provided with pipelines, tube trailers and on-site, and also one example that's pure pipeline only. And I guess the aim to do this and what we're sort of planning to evolve in Alpha is to refine this and allow comparison. I think if you can go back one to, on mine it's slide 14, yeah, that one. So here's these scenarios that were modelled. Effectively what you can see is hydrogen being generated from these major hubs in the rollout phase, and the sort of point sources that it's effectively most cost effective for those stations to supply. So the modelling tool is aiming to minimise the system's costs of supply. What you start to see, so in the sort of rollout phase, it's fairly doable to supply with tube trailer technology, but in the mature phase, you'll start to agree that those kind of lines are getting incredibly busy. And actually what we learned was that station sizes start to become so large that sort of truck and tube trailer deliveries become both kind of operationally difficult to manage in terms of the number of deliveries per day, and also not cost effective. So if you go on to the next slide, what we have here is the overlap of the pipeline or the planned hydrogen pipeline infrastructure and those mature hydrogen stations. And what you can see, and probably won't come as a massive surprise, is that the strategic road network is fairly well linked with the pipeline network plans. And so there is a real kind of strategic case here for hydrogen stations being able to be connected to hydrogen pipelines. And this, as industry has shown over a number of years, is a really cheap and cost-effective way to supply kind of large sources of demand with low-cost hydrogen supply. And the model kind of bears that out, that effectively scenario 3 is the lowest cost method of supplying those hydrogen demands. And so if we go on, finally, I guess I can just talk a little bit about those overarching conclusions. This is more just, I guess, what I've talked to already, which is that we see the future of the gas grid and the road network looking something like large point production sources around the industrial clusters. Even some small stations that are located close to those clusters being cost effectively supplied with pipelines. And effectively that's a kind of low regrets opportunity. As hydrogen demand ramps up, those pipelines will obviously be able to supply more hydrogen cost effectively. So this was, I think, one of the emerging conclusions that we interestingly kind of didn't necessarily set out with, but that there was something that we've evidenced, and I suspect a lot of the gas networks have kind of talked about, but that there is a real case commercially for the gas network to supply hydrogen to these large stations. And so what we did in work package 4, if you go on to the next slide, was start investigating a real world case that we can develop through the sort of alpha and beta phases to show off a world first design of a station that is directly linked to a hydrogen pipeline. And through this kind of stakeholder engagement, we identified 6 potential projects, each with a number of partners in that we've had to redact for confidentiality reasons. But in theory, these are all kind of potentially prime sites. So they are large vehicle deployment plans located not too far away from plans for a large hydrogen production source, and therefore are kind of prime candidates for a first hydrogen refueling station linked to a pipeline supplying hopefully a multimodal demand for hydrogen transport. So going on then into the alpha phase, our plans then and coming sort of the end, what we have and what we set out with was developing this Athena model to facilitate a kind of more collaborative and coordinated planning approach between transport and the gas networks. And we plan effectively to carry on the same 4 work packages that we had developed and split them out effectively along a line of strategy and modelling and feasibility. So these are the first, these are the strategic work packages, which is effectively around building on this Athena model. So refining the data sets, potentially including other modes of transport, things like coaches, landside, airport demand, and potentially trains. Starting to make the model looking at today's policy focuses to get a sense over the next 3, 4, 5 years where the system will develop, and then showing off kind of more incremental scenarios for the development of that system. The dispensing, it's around kind of understanding and refining those station locations based on model scenarios and sensitivities, and getting a slightly more refined kind of station capital and operating costs. And I think the real useful part of this or output that comes out effectively is being able to use the Athena tool to show different sort of rollout scenarios and hydrogen pricing and development scenarios, and comparing those different scenarios. And what the tool will give us is an optimized system cost that minimizes the total hydrogen supply cost. So at the end of the day, the end beneficiary of this whole project is transport users, and effectively a well-scoped and well-designed gas grid supplying hydrogen will benefit them by reducing the cost of hydrogen supply. So in terms of work package 4, then it's just about disseminating this information. Clearly, we're focusing on the northern powerhouse regions, but this plan can obviously be replicated and probably should be replicated across the other GDNOs, and looking to share those informations. And then if we go on to the last slide, the other aspect of this is around the feasibility. So I've already talked about how you might develop this along the lines of a real project for real demand. So we're looking to really join up SIF funding with a number of other funds, things like zero emission bus funding, zero emission truck funding, the Tees Valley hydrogen vehicle operators, create a viable sort of total cost of ownership case. And that's obviously crucial. As I said, they're the end consumer. So linking those vehicles with a kind of contented TCO to hydrogen refueling station suppliers, and then obviously looking to joining up with large scale hydrogen production hubs via a pipeline is exactly what this project wants to do. And effectively, we see this as a world first chance to evidence the gas grid's capability of supplying future decarbonised hydrogen transport demand and supporting and de-risking the conversion of the gas grids to net zero. Thank you.
Thank you, William. We're now coming on to the Q&As finally. So what I would do is I will welcome back everybody and any of the lead networks. Perhaps you can put your videos back on and we can have a few questions. We'll do some individual project questions and then we'll try and do some cross theme questions. So is Colin still on the call? Yep. Yeah, great. Great, Colin, I just couldn't see you there. Just coming to your project, first of all, I know that you've answered some of the questions in the chat, but if you could just sort of answer them out loud so that everyone on the call, just in case they've not picked them up. So how transferable are your cost assessments for other lines? Is there an exercise that would need to be repeated for similar archetypes, or is there a learning that can be streamlined, that can streamline the process in the future?
So we've attempted to try and be able to do that because we see and actually started to realise throughout the project that this collaborative way of thinking to decarbonise the railway was included in the UK policy, something called the Traction Network Decarbonisation Strategy, which is something the railway colleagues on the call will recognise. But we did some of the studies for that that underpin that, and we were told not to include the energy supply aspects. So there has been a quite big kind of missing link here. So we think that the lines that are currently kind of indicated as might be suitable for hydrogen, if you include the electricity supply costs and alternatives, that map might change, the map that I showed you with the lines in red, green and yellow. And this project and the other two projects, I think, are starting to create the evidence base to move that, which means more lines, coming back to the question, and making sure these assessments can be reapplied. We did 2 lines, partly for that reason, but hopefully it could be transferred to others, and we're starting a conversation already about some of those for another part of the UK to test that out.
Great. So I think what you're saying then, Colin, is certainly within your project, and perhaps the other rail decarbonisation projects can comment, but your CBA, your cost benefit analysis, is taking into consideration other energy pathways such as heating, industry, that sort of thing as well. It's considering the local landscape.
No, not heating. It is about fuel for the railway. Clearly, if the scale of hydrogen demand locally for other forms of transport like road, as covered by the last project we heard from, and heat, then that would increase scale and reduce costs of hydrogen. We have not assumed substantial costs of hydrogen reduction over the 30-year lifetime. We were pessimistic on that.
Thanks, Colin. We might come back to you in just a moment. We'll just make sure, I just want to make sure I can get questions to everybody here. So coming to the multi-energy hub networks then, how would the customer relationship between station owners and train operating companies, how would the relationship work between the station owners and train operating companies? I'm wondering what the commercial arrangements might be for work in the rail industry.
Yeah, thanks, Kate. Kang, do you want to take this, or shall I take this one?
Yeah, I probably can kickstart, and I think yes, absolutely. You're and David raised the quite right about the questions of the commercial arrangement. I saw first is that this is one of the actually the complexities and issues we identified in the discovery phase, and also raised by real industry partners. In the hub project, we look at both the traction and the non-traction power supplies, from but also we look at for example, the EV charging potentials at the car park. So it involves both. Lots of stations. We know that now they're owned by Network Rail, but they're operated by TOC, many of them. So and then the projects of the car parks that involves actually private sector. Probably they're owned, operated by that car park owned, operated by private or other unit utility or owners. Hence, this is one of the issues we identified, and we hope that through the other phase will work with the different owners and stakeholders, including Network Rail, TOC, and other sectors to develop a suitable business model work around this. Nick, Matt, you want to add more on it?
I think, yeah, just to add to what Kang said, that obviously we're working with Network Rail, who have potentially identified from the stations that we looked at in the discovery phase a number where they own the land, unused land around the stations, and also some of those, for example, Bar Hill already have renewable energy wind farms nearby. So we've already sort of tried to identify ones where this will not be a huge issue to start with, and once we can demonstrate the viability and everything of it from in the next alpha phase, then hopefully more people will buy into it from there.
I would like to add more. Actually, in our discovery phase, we have you probably have seen the 4 scenarios we have designed. Scenario 1, which is only cover the station, and and then the station scenario 2, which covers the nearby the car parks, and then station 3, which covers actually also consider the recovery, the traction power, regenerative power from the trains. So involves actually high voltage. And the scenario 4, we look at the rural stations where, as identified also by the hydrogen project, 2H project, Colin has presented. So we look at different scenarios, and hence the complexity in also the stakeholders involved in different scenarios are different as well. So when we roll out the technology, we actually will tailor our solutions for different stations, because different stations, they have different stakeholders, and then therefore we'll carefully consider this in our phase and the roll out as well.
Thank you. Okay, just moving on to the other rail project then. So Sarah, how can you keep such a dynamic tool given the rapid developments in the energy sector? Is there an opportunity to identify key tipping points that might drive significant change in rail decarbonisation strategy?
Yeah, I mean, that's a valid point because network capacity is always changing. I suppose the initial phase would be to map the network data provided by the local DNO as it is standing currently. But then I suppose to progress beyond that would be to update it. Obviously, if there was a business case for that, is being developed for other software that EA are producing, so it would be, updated on a regular basis if there was a need for that moving forward. But yeah, that is a valid point. It is dynamically changing, and that's the challenge that we're facing.
Thanks. This might be a question for all the projects, but are there least regrets options that rail can progress regardless of whether power or hydrogen strategies are progressed? Any takers?
Good question. Genuinely holistic. I think, I guess I kind of approach this from the point of view that the railway has many features that are unique, but one of which is the long-term nature of the railway as a transport mode, the long life of the vehicles, and therefore the choices that the railway makes have an influence into other sectors and other transport modes, which slightly links to some of what William was talking about, that the railway choosing a fuel for a particular line like hydrogen and therefore requiring hydrogen production, hydrogen refueling, will be a catalyst for other sectors to choose hydrogen. So I guess we approached it from that sort of line of thinking, which is partly answering the question, I hope.
Yeah, and Sarah, in terms of your project, how would the tool feed into those strategies?
Into the hydrogen strategies.
Into the hydrogen and electricity development, strategy development more broadly.
Yeah, would take the sort of the long-term development strategies from the energy networks and feed that into it, because obviously which I don't think it came across in the presentation, we are looking at developing scenarios for each of the decarbonisation solutions, so short-term and long-term.
Thank you. Okay, let's see. We've got one for all the rail projects again here, and then we'll come on to William, who's been patiently waiting there. So I'd be curious to hear views on the pros and cons of looking at rail directly versus whole system analysis, which I do appreciate might introduce major uncertainties and assumptions. And we've got an audience member who's keen to understand the best way to approach this problem.
So a bit of background, which I don't think we've probably explained. So the discovery phases were 8 weeks and therefore had to be quite focused in what they were doing to kind of make some progress, to start a project, recruit your stakeholders and move on. And I think although there was during the discovery, and this event kind of further takes it forward, some interlinking between the projects, I think there is definitely now a bit more time for reflection about what does the combined set of results start to tell us, and does that bring out ideas and paths forward that we didn't spot individually. And I can, from this morning's session, I can already see some of those themes. Again, that's possibly not fully answering the question, but hopefully it's an interim one, given the state of the game at the moment.
Well, I would like to add probably on Colin's comment. The HUB project, really, if we start this project, we actually, the ideas originated from the, through the Europe, this called the transit-oriented development, which is to, pretty much high on the agenda of the UK and European cities, which does look at this station as well as this role in the development of the city, and we identified that though this called TOD or transit oriented development is high on the agenda in the UK and Europe, but the significant efficiency and the flexibility potentials to benefit the power industry, as well as the city has not been fully properly explored. And the hub, I believe, this is just a small step to look at the whole system approach and how the decarbonization of the rail around the station, which is got the 10,000 miles, we got the 2,500 stations linked to the cities, linked to the transport, the cities, but also we got the route, which is the H2H and other projects added the route as well. So hopefully when we work together along this project, we'll see how this, we'll see how the outcomes from this project, and then see how this whole system approach could be taken forward. Hence, broaden the impact as well as to reassess the CAD as well. So that's my point.
Thank you, Professor Lee. I'll just check, Sarah, would you like to add anything?
No, I think it's been covered, but it's just about really just making sure that you've got the boundaries in place, system boundaries. Otherwise, I suppose it can get very complicated.
Okay, last one on the rail one then. So what changes will be needed to the gas network to limit any hydrogen leakages? Quite a specific question there.
I think that might be more of a networks question.
Do you want me to pick that up, Kate?
Yeah, you go, Dave.
David.
Yeah. Hi, David Gill from Northern Gas Networks. Thanks for the presentations, and I'm sure most everybody on the call will be aware of the work that's being carried out on the existing 330,000 kilometres of gas pipes that are in the deck at the moment, on the suitability and feasibility of carrying 100% hydrogen. There will be a report that comes out the back end of this year, which shows, and everything so far is showing that with some tweaks to that and replacement of some of the network, that we will be able to distribute 100% hydrogen down those networks, that amount of network. What it also allows us to do we've got projects like this, both in the rail and the one that Will's just described there, and the multimodal for transport. It'll allow us to prioritise where that reinforcement or changes of size of pipe, etc., or type of pipe, where that can take place. So all these things overlap. So we're confident as a Cadent and SGN and Wales and West and National Grid that will be able to happen and be able to repurpose the network to run 100% hydrogen down those pipes. There will be some things we need to do, as I said before, and that will come out in the wash. But that will be feasible for us to do.
Thanks, David. Okay, coming on to William, we've got a fair few questions for you, William, so we'll try and rattle through some of these. So where does the relative cost risk of creation, distribution, storage of flammable fuel sources versus electrification come in? That was a long sentence.
Okay, so the cost risk in terms of factoring in safety features, I think, to be honest, it's obviously factored in all the way along the line. I mean, the gas network currently obviously also transports a flammable gas, and CNG stations are familiar with those kinds of cost risks. So in short, I think it's shared evenly along the supply chain from producers, suppliers and distributors.
Thank you. With the EU suggesting a maximum value number of trucks of 100,000, I think it says 100,000 and 200 hydrogen stations in Northern England, seems likely to be an oversupply. I think it's more of a comment than a question. Unless I've missed part of the question there, maybe somebody can correct me. We'll move on to the next one if there's nothing to add to it. Have you considered the impact of liquid hydrogen on lowest cost to serve this HRS network?
Yeah, that's a really interesting question. So we have sort of circumspectly, I think the timeline that we had and the scope in Discovery didn't really allow us to do a proper cost analysis. So that is something we want to build into the alpha. At this point, obviously, liquid transport is still kind of somewhat a technology of the future in terms of truck trailering, but it does seem to be that the next generation of stations is going to look at that, and I think there is a genuine uncertainty around whether it's liquid or gas networks, and effectively the next 3-4 years will show some evidence of pipelines versus liquid.
And I think this is the last question we've got time for here. So does the forecast model consider social aspects of hydrogen uptake and the time it takes for sectors to uptake new technology? So it's meaning like skills, safety protocols, etc.
Yes, so there's some funding coming out in the Tees Valley to develop a kind of skills and innovation hub in and around the Tees Valley. So I think clearly there is a very important piece of work that needs to go on around the socialization of hydrogen technology with people. People still think of the Hindenburg when you say hydrogen, which is a slight hindrance. So the model can't really incorporate human sentiment towards hydrogen technology, but I suppose the idea is once the snowball starts to roll downhill and everyone sees hydrogen buses operating in cities, that the sort of fear factor for that starts to move away. So it is more or less based on sort of predicted hydrogen vehicle production and obviously decarbonisation targets rather than human sentiment analysis.
Great. Thank you, William. I'm getting nudged, we're behind time, so that is all we've got time for on the questions, but thank you very much for the speakers that we've had this morning. Again, the slide deck will be shared and so will the recording. We're going to take a wee break now. I think it's still 10 minutes. Chris, can you keep me right?
Yeah, I think we've got time for a 10-minute break.
So on my clock, it's 10:27. So we've got a lot still to cover. So it will be back at 10:37 for the next presentation.
Okay. Thank you, everyone.
Thank you.
Thank you.
Bye.
Thank you.
Thank you.